To week 6 of the Scuba Educators International Equipment Service course taught by Scientific Diving International. I'm Dan Morelli. I'll be teaching today, and hopefully you'll learn something very interesting about gauges and hoses. Safe diving requires that divers monitor their depth, bottom time, and gas supply. Pressure gauges are used to monitor depth and gas supply. Robert Boyle, the same person who developed Boyle's Law, created the first underwater depth gauge in 1659. It consisted of a curved glass tube closed on one end, and when the tube was taken underwater, the airspace in the tube got smaller as the pressure increased. Now, the interface between liquid and gas we often call the meniscus, and when you're reading a graduated cylinder or something like that, you look at the bottom of the meniscus. So the meniscus is going to move as the pressure goes up along the calibrated tube, and that told people how deep the tube was. It wasn't a very practical depth gauge, but Boyle did invent one. In 1849, the Bourdon tube was invented, which led to practical and accurate pressure gauges, and it's still used today. Depth gauges were an integral part of scuba diving from the very beginning, but pressure gauges used to monitor cylinder supply pressure did not become popular in the United States until the late 1960s. The submersible pressure gauge, or SPG, became an essential piece of scuba equipment in the 1970s. So let's find out a little bit about how pressure gauges work. The simplest pressure gauge is the capillary gauge, which uses the principle discovered by Robert Boyle in 1659. A tube closed on one end, opened on the other, is taken underwater, and as water enters the tube as a result of increasing pressure, we read the meniscus as it's going around the calibrated dial. The capillary tube or gauge has no moving parts, and it's relatively inexpensive. Very inexpensive they were. The problem with capillary gauges is that they're inaccurate or more difficult to read at deeper depths because the rate of pressure change is less at deeper depths, and the scale gets very crowded as the gauge gets into the deeper depths. So it's really good for shallow water, but not so good for deeper water. So capillary gauges were inexpensive, but they're no longer produced by diving manufacturing equipment makers. However, recently a very expensive watch came out with a capillary depth gauge on the inside of the dial, and this one is called the Oris, and you can see that the capillary gauge is in this case calibrated in meters of seawater. Surface applied divers use a version of the capillary gauge, and part of the surface applied diving hose is an open hose that's attached to the diver, so the diver carries it with them to depth, and the people on topside will open up a valve and pressurize that open-ended hose to ambient pressure. The diver tells topside when they see or feel bubbles coming out the end of the hose. They turn off the gauge, or the valve rather, and the very accurate gauge on the deck or on the dock will read feet of seawater or meters of seawater, and this gauge is called a pneumofathometer. So it might be old technology, but it's still being used, and you can see that this is a very accurate gauge, the pneumofathometer, and they're calibrated. But let's talk about gauges that are more commonly used by modern scuba divers. One of those types of gauges is the diaphragm gauge. Diaphragm gauge uses a sealed container with a flexible diaphragm on the back side of the gauge, and as pressure increases, the diaphragm is pushed inwards. The diaphragm activates a gearing mechanism that causes a needle to move and indicate depth. Bourdon tube gauges have a flattened tube arranged in an arc or helix that tends to become round under pressure, so it tries to deform when it's pressurized. it tries to straighten itself. And if the gauge is calibrated correctly, the mechanical motion that is created by this moving Bourdon tube is used to move gears that cause a needle to move and indicate depth. Digital gauges use a transducer to measure pressure and convert it to voltage. The depth gauge is a pressure gauge, calibrated in feet or meters of seawater. Analog depth gauges primarily use a Bourdon tube to transfer pressure to mechanical energy. And there are several kinds of Bourdon tube type depth gauges. Oil-filled depth gauges use a diaphragm or the flexible plastic case itself of the depth gauge to transfer pressure through oil and externally to a sealed Bourdon tube. So the pressure is coming around the outside of the sealed Bourdon tube. As pressure increases, the Bourdon tube tries to straighten and causes a needle to move and indicate depth. And here's a picture of a Bourdon tube oil-filled depth gauge from the back, and you can see that copper-shaped arc is the Bourdon tube, and it's connected to a gearing mechanism which causes the needle to move. And on the right is the face of an oil-filled depth gauge. Now, oil-filled depth gauges have linear scales since oil is not compressible. Gas-filled depth gauges use a helium-filled bladder that compresses during descent and pressure increases. The helium is forced to the inside of a Bourdon tube that's open on one end, causing the tube to change shape and move a depth indicating needle. So the action is very similar. In this case, though, the pressure is coming from within the Bourdon tube, inside the Bourdon tube, rather than outside. Gas-filled depth gauges have nonlinear scales since needle movement is related to the rate of change, and pressure rate changes faster in shallow depths. So we can see on this gas-filled depth gauge that the scale gets closer together the deeper the diver goes. Gas-filled depth gauges are highly accurate in shallow ranges, and some are altitude adjustable. This one happens to be altitude adjustable. Companies such as Aqualung, XS Scuba, Sherwood, and Scuba Pro, and others offer gas-filled depth gauges. Some of them have maximum depth indicators like these gauges on this page do. Digital depth gauges include those on watches and dive computers. Use a pressure-sensitive transducer that converts increasing pressure to voltage. The digital depth display increases as voltage increases. And digital gauges can also display maximum depth, bottom time, and water temperature. Here's an example of a digital depth gauge. Depth gauges should be checked for accuracy at least once a year, or at least when the regulator service is performed. Now, some manufacturers will allow a 2-year service interval, and so that would be the time you would check your depth gauge. There's no way to calibrate an inaccurate depth gauge. A depth gauge that reads slightly deeper is acceptable, since that would be conservative, but a shallow reading depth gauge is unacceptable, just like a slow running watch. Some gas-filled depth gauges are altitude adjustable and can be adjusted for either altitude diving or changes in atmospheric pressure. Capillary depth gauges automatically adjust for altitude, but have recognized drawbacks. We talked about those earlier. Depth gauges are checked for accuracy using a pressure test chamber. Pressure chambers use very accurate test gauges that are regularly calibrated. Watches and computers that rely on water for actuation need to be submersed in water in the pressure chamber. And here's an example of a modern pressure test chamber that's used to test depth gauges, computers, and watches. Submersible pressure gauges or SPGs, monitor the cylinder supply pressure. The SPG is based on the bourdon tube, pressurized from the inside by high pressure supply pressure. And you can see that in this SPG that's been taken apart, there's what looks like a coiled up spring in the middle of the gauge. That is not a coiled up spring. That happens to be the bourdon tube. And as that bourdon tube gets inflated from the inside by HP supply pressure, it's going to move that needle as the bourdon tube tries to straighten itself out. Many submersible pressure gauges, even today, are analog and use a rotating needle. The pressure indicated by an analog SPG is a relative measure of the gas supply. So maybe not highly accurate, but it's good enough because we're always giving ourselves a buffer of at least 500 psig at the end of the dive. So it may not read accurately to the nearest pound per square inch or bar, but it's good enough. SPGs can be made of plastic, chrome-plated brass, or stainless steel with a glass or plastic lens. Metal-bodied SPGs last longer, simply because the plastic case is susceptible to cracking if you knock it on something or drop it or somebody steps on it. It's just, a matter of fact that metal is going to be a little bit more rugged. The submersible pressure gauge has a built-in overpressurization relief system. Typically, this is a plug of rubber or plastic that's inserted at the rear of the SPG case. And the purpose of the overpressurization relief device is to prevent the SPG from exploding in case there were a high pressure leak inside of the case. If the bourdon tube was damaged or for some other reason HP gas was getting into that case, that's going to turn into a very dangerous device. So the submersible pressure gauge pressure relief device is designed to blow out. Now notice that if that little piece of rubber or plastic comes out, it's going to come out like a BB. So when you're pressurizing a SPG, you want to make sure you turn that back of the gauge away from people. And in this picture, you can see the little overpressurization relief plug at the back of the case of this SPG. Digital depth gauges can be standalone or incorporated in a dive computer. And as we mentioned earlier, they could also be part of a watch. Citizen makes a watch called the Aqualand that has a depth gauge built into it. Digital SPGs can be hoseless, using a transducer to deliver through water signals to a wrist-mounted or console-mounted unit. The transponder must be paired with the computer on the surface. So that's something that you've got to do when you get a hoseless computer. You need to do that pairing before you go out to the dive site. Computers can display all kinds of additional things besides just cylinder pressure. They can display how much breathing gas remains, as well as, and that is dependent upon depth. So it's going to actually track your breathing rate and determine how fast you're using up your gas. And so it'll tell you how many minutes you have at a certain depth. And it will also, computers are also going to give a estimation of your decompression obligation. And here's a couple of examples of submersible pressure gauges, the Shearwater on the left and the Suntow on the right. I'm not favoring any brands, I just want to show you that there are different ones out there. And these are both hoseless. Let's talk about pressure hoses. Regulators use both high pressure and interstage pressure hoses. Hose design and construction has changed very little in about 50 years. And the reason for that is these hoses are very reliable and very rugged. And so the manufacturers really don't have any impetus to do anything different to the hoses than what they've done for the last 50 years. The basic hose design is an inner layer of neoprene or EPDM rubber These are both artificial rubbers, so they're going to last a long time. They will not be broken down by the oils of your skin, and they're resistant to UV and things like that. Outside of the inner layer of rubber is a nylon mesh that's braided over the inner layer. It's a strength member. And then outside of the mesh layer of nylon would be a second layer of rubber. So here's a cutaway, literally taken by using a razor blade or a utility knife to cut away some of the sheathing, so you can see what the construction is. I've cut away the rubber outer layer. You can see the braided nylon that's surrounding the inner layer. And in the picture on the right, you can see the two layers separated by the layer of braided nylon. So that's basically what a interstage pressure hose looks like on the inside. The force that's being contained inside that hose is primarily held back by the inner layer of rubber and the mesh. So if you have a small nick or cut or scratch in the outer layer, it's not going to cause a leak, but with the caveat that if you have any kind of damage to that outer sheath, it's time to replace that hose. Hose pressure ratings are stamped or stenciled on the hose exterior. And since some point in the 1970s, the fittings and the size of the hoses are different so that you cannot interchange them. You cannot thread a high pressure hose into a low pressure port or vice versa. High pressure hoses have very narrow diameters and even smaller supply hoses. As you can see in this picture, there's a very, very tiny hose down the center of that fitting, because the volume of gas going to the submersible pressure gauge does not have to be a lot. We just have to be able to sample it. And if you had a high pressure leak with a large volume, that would be very seriously bad. So they keep those diameters very small. Some hose designs, some manufacturers use a single layer of a urethane material surrounded by a braided nylon mesh. So instead of two layers of flexible material sandwiched around a nylon mesh, this has one layer of flexible material, in this case a urethane, surrounded by a braided nylon mesh. The purpose of this is to provide a more flexible hose. And of course they get all these different colors in the nylon mesh as well. But these particular hoses have had problems. Some of them have broken down, especially in places where you have a lot of heat like Florida. The inner urethane crystallized, turned into little particles, and jammed up the entrance to the second stage. That's not the kind of hose material that you really want to use. The manufacturer has recognized that there is a life to this hose material, and they recommend replacing them every 5 years. Rubber hoses do not have a recommended end of service time. Hose protectors can extend the life of regulator hoses, particularly where the hoses are threaded into the first stage, because that's a place where a lot of strain is put on the fitting. Particularly if you don't have a swivel with a standard or unbalanced regulator, there's going to be a lot of bending right there where the hoses come out of the first stage. So use hose protectors. They'll make the hoses last longer. Hoses use straight O-ring sealed threads where they join the first stage. The intermediate pressure inflator hose ends in a quick disconnect fitting. We talked about that last week. The regulator interstage supply hoses end in a swivel fitting with a captured O-ring that seals on the inside of the second stage air barrel. So that stops gas from leaking out, but it allows the second stage to swivel on the end of that hose. And when we get to the hands-on part, we'll show you how to get that little O-ring out and put it back. High pressure hoses end in a swivel fitting with a device known as an air spool. And I've got two different kinds of air spools on this picture. They both do the same thing. The air spool does a couple things. It allows gas to pass down the center of it. It's got a hole drilled right through the center of it, and that gas is going to the submersible pressure gauge. It also permits the fitting to swivel so that your gauges can swivel on the end of the high pressure hose. High pressure hoses tend to be a little stiff because of the amount of pressure that's inside of them. And the air spool also seals the fitting on both ends. So at the end of the hose and on the inside of the submersible pressure gauge, there's a little O-ring that's holding back up to 3,442 psig of pressure. So we're relying on those little tiny O-rings, and they do wear out, which we'll talk about in a little bit. The size of this O-ring is a 003, and O-ring sizes are the numbers that are assigned to them are indicative of the diameter of the actual rubber ring and the width of the entire ring. So if you put it down on a piece of paper, you can say that's a 3, that's a 10, that's a 6, but the first letter, the 0, indicates the diameter of the actual. If you cut the O-ring in half, that's the diameter of that ring. So that there shouldn't be any mystery to that. Now, fittings at the end of hoses are constructed of chrome-plated brass. Each fitting consists of a metal barb that is inserted into the inner diameter of the inner hose. Then a metal collar is squeezed down progressively to a smaller diameter with equal pressure from all sides, trapping the hose material between the barb and the collar. This is a process known as swaging, and it creates a strong, gas-tight fitting. So that's the barb fitting. This is the collar. Field care and maintenance. When you rinse and soak your regulator, you're rinse and soaking your hoses and gauges. And we want to do that every time we've been diving in pool water or salt water. Not so important in fresh water, unless there's something particularly wrong with the fresh water you've been diving in. Just remember that gauges are sensitive to impact, especially computers and depth gauges. So you want to use care when transporting or stowing. Plastic body gauges can crack if dropped or banged. Use caution. Inaccurate gauges must be replaced, but most gauges will last a long time and stay relatively accurate. Hoses rarely cause problems, but examine your hoses prior to a dive trip and replace if the outer sheathing is damaged, or if you see that the outer sheathing has pulled back from the collar of the swage fitting. That's the time when you need to replace those. A few hoses have separated from fittings over the years, and it's very few, but if it were to happen, it would be a very, very dangerous thing if it was an intermediate pressure hose, for two reasons. Number one, the contents of the cylinder are going to go out the end of that hose very, very quickly. I did an experiment years ago, and a full aluminum 80 at the surface with a severed hose will not last more than 6 minutes. So if you're at depth, it's not going to last very long at all, especially if it's not the beginning of the dive. The other thing is that hose is going to be whipping around like a coach whip, and it's going to have a lot of force behind it. And so first of all, you got to get your buddy over there to get to share air and get the regulator turned off so you stop that hose from whipping around. If you find that a hose is weeping small bubbles through the outer sheath, replace it. Now, I have to mention something. When you first get in the water, sometimes little tiny bubbles get squeezed out as the hoses get compressed because air has leaked in to between the layers, and that's okay. If that happens, that's fine. You see little bubbles stuck to the outside of especially the high pressure hose, it's not an issue. But if they continue to weep out over time, then you've got a small leak and you need to replace that hose. There is one particular leak that we can easily fix in the field if we have the proper tools and the proper expertise, and it doesn't take a lot, but we'll go through that. And that would be a leaking air spool on the end of the high pressure swivel, or a leaking high pressure or interstage pressure O-ring. If we've got either of those, turn off the cylinder and depressurize the regulator. Use a proper wrench to remove the hose where it's leaking. Most high pressure hoses are going to use a size 011, a 011 O-ring where the hose joins the first stage. Interstage pressure hoses generally use a size 010 or 010 hose where it joins the first stage. 010 O-ring, sorry. Inside the intermediate pressure hose where it joins the second stage of the regulator, as I said, there is a captured O-ring, and it's a little bit tricky to remove it. Once you learn the technique, how to do it, it's not bad, but you got to have the proper tools and a little bit of expertise to get at that O-ring and change it. And that's one of the things we'll cover in the hands-on portion of the course. Some manufacturers use special O-rings there that aren't the standard off-the-shelf 010 or 011, and then you have to make sure you have the proper O-rings in your dive master kit. The air spool O-rings, which is inside the HP swivel, are the most likely of O-rings to leak because they're holding back at least 3,000 psi G every time you pressurize the regulator. And so they're the ones that are going to fail the soonest, and typically they last maybe a year, and then you have to start replacing them. Inside the high pressure fitting is the air spool. I showed you a picture of that earlier. The O-rings are size 003 and are difficult to install unless you use a special tool called a bullet. And the reason for that is they're very stiff and very small, and to get them to stretch over the end of the air spool using just your fingers is virtually impossible. I mean, it is possible. It will frustrate you, I will tell you that. So you want to make sure you have the proper tool. Have a dive master that's trained in how to change these O-rings, or other technicians show you how to change the air spool O-rings. And here's an example of the bullet, which is this conical nylon piece here. It's got an O-ring stretched over it. You see how wide that is compared to the standard size of the O-ring, so it stretches it out so it can slip over the end of the air spool, and the air spool is mounted inside this piece of nylon here just to hold it in place. Here's another air spool just sitting here. We could do the same thing with it. So these O-rings come off. These are the new ones, and we lubricate them and use the bullet to easily slip that O-ring on there. All right, so depth gauges need to be checked for accuracy every year, or at least when the regulator is serviced. Replace an incorrectly reading gauge. It might be rare, but it does happen, and so that's why we have to check. Examine hoses and fittings for damage or wear on a regular basis, particularly if you're going to go on a dive trip somewhere. You want to make sure that your hose isn't going to be something you have to replace out in the field. Get it done before you leave home. And the only downside to doing the presentation like this is you people can't ask questions in real time. So I expect that you'll be sending me texts and emails if you have questions based on this lecture. And next week we'll be talking about alternate air source inflators.